Let's take a moment to go over the double slit experiment again mathematically. First, let's discuss why we expect to see an interference pattern. The light is shining onto these two slits from the left. Once it passes through the slits, the light fans out, hitting the wall in a bunch of different places. I've drawn two example light rays that are converging on this point on the wall. The distance that the two light rays travel is different. We know that when waves travel different distances, they will interfere in interesting ways. How different those distances are depend on where on the wall we're looking. If we look straight ahead, the distance that the light rays travel is the same, whereas up here, it's not the same. Let's analyze this mathematically. Something to note is that this is not at all drawn to scale. Remember, when we did the experiment in the lab, this distance was about 2 meters. Hopefully, you are able to calculate that the distance between these two slits was only a fraction of a millimeter. In other words, this distance is thousands of times larger than this distance. I can't fit that on a whiteboard, so we just have to draw it like this. In order to determine the kind of interference that the two waves experience here, we need to determine the difference in the distance that they travel. It turns out that these light rays are almost exactly parallel in real life. Of course, we can't see that here because we can't draw them to scale. Let me draw in a little something that will help us see what this means. Once the light rays pass this dotted line, they are effectively traveling in parallel until they reach the wall. This means that past this dotted line, the distances that the waves travel are the same. So the only difference in the distance is this little leg of this triangle here. This lower wave is traveling ever so slightly farther than this upper wave. Let's calculate what this distance is. To do that, let's label a couple of quantities. The distance between the slits we're going to call lowercase d. The distance from the slits to the wall we'll call uppercase d. Lastly, we'll call this angle here theta. It turns out that if this angle is theta, then this small interior angle is theta as well. Let's think for a moment about why this is. This angle theta is created by these two lines. Notice that this black dotted line is perpendicular to this line, and this black solid line is perpendicular to this line. This means that the relationship between these two lines must be the same as the relationship between these two lines. This means that this small angle here is also theta. There's a lot going on in this diagram, so I'm going to remove a small piece of it and draw it down here. This distance here is the difference in the distance that the individual light rays have to travel to get to the wall. We can use geometry to figure out what this distance is. Recall that we're labeling this distance between the slits as lowercase d. We have here a right triangle, so we can use sine or cosine to determine the relationship between this distance here and this distance here. In this drawing, the distance between the slits is the hypotenuse of the triangle. In this case, we need to use sine to relate this distance to this distance. The sine of an angle is equal to the opposite edge of the triangle divided by the hypotenuse. This is the angle we're interested in, so the opposite edge is this edge, and the hypotenuse is this distance d. We'll call this distance delta x. So writing it out, this says, the sine of this angle theta is equal to delta x over d. Let's see if we can relate the angle theta to some other numbers in our problem. Remember that this angle is the same as this angle, so we should be able to relate these distances to this angle. D is just the distance from the slit to the wall. But we need one other piece of information, and that's this distance here. Whenever there are two slits, there will be a bright spot right in the middle of the pattern. Let's pretend that from here to here is the distance between the central bright spot and the first bright spot above it. We can relate these distances to the angle theta. If we call this distance y, we can relate this angle to these two distances by using tangent. The last thing we need to know is under what conditions we will have constructive interference. Constructive interference occurs whenever the difference in the distance that the waves travel is equal to an integer number of wavelengths. For the central bright spot, the difference in the distance that the waves travel is just 0. For the bright spots directly above and below the central bright spot, the difference in the distance that the waves travel is just 1 wavelength. For a laser, that was 633 nanometers. For the second bright spot above and below, this difference in distance is just 2 wavelengths. For the third, it's 3, and so on. So we can write that generally like this. This is just the condition for constructive interference. The difference in the distance the waves travel is equal to an integer, n, times the wavelength. Let's use these three equations to solve for the distance between the slits in terms of the things we're actually able to measure. To do this, we need to know an interesting result from geometry. If you'll recall, the distance between the bright spots was extremely small. I very much exaggerated this angle for the purposes of being able to draw triangles. But in practice, this angle is extremely small. It turns out there's a result from geometry known as the small angle approximation. It turns out that for very small angles, the sine and tangent of the angles just equals the angle itself. So we can rewrite these like this. Remember, these are just approximations, but for our purposes, it works to write them out like this. Because this number and this number are both equal to theta, we can set them equal to each other. We also know what delta x needs to be for constructive interference to work. It just has to be equal to an integer times the wavelength. So let's replace delta x in this equation with n lambda. Remember, we're trying to solve for the distance between these slits because it's too small to measure them directly, but we can measure these other numbers. So let's solve this equation for lowercase d. And there's our answer. The distance between the slits can be found using this equation. Something to note is the presence of this value, n, here. In this case, n tells us which bright spot we're looking at. The central bright spot corresponds to n equals 0. The first bright spot corresponds to n equals 1. The second bright spot corresponds to n equals 2, and so forth. In our experiment, we measured the distance between the central bright spot and the first bright spot above it. So in that case, n is just equal to 1. Y is the distance between the central bright spot and the bright spot that we happen to be looking at. So even though n can take on a bunch of values, y can take on a bunch of values too. In order for our approximations to be accurate, though, we need to be measuring near the central bright spot. That's why I measured the first bright spot above the center. So far, we've been primarily focusing on waves that are traveling from one place to another. But there are other kinds of waves we can consider, and we'll see those in the next DL.